It's really a great thing to see him as listed as a lead physicist for quantum computer at a Quantinuum. And I think Stephen's going to tell us about how to scale up quantum system. This is a critical part of building the modern quantum computer. How do you get more and more qubits together? But also, equally as important, how to benchmark systems like that and run quantum circuits on the current quantum machine. You don't want to keep building without running some quantum circuits and find out how the machine is responding to the current algorithm and so on. So Stephen's going to touch on both. Let's give him a hand and welcome you back.
Okay, I mean that's working okay. So thanks, June, for the kind introduction. It's great to be back at Gilla and see you. And yeah, so as June said, today I'll be talking about our recent work at Quantinuum on developing and benchmarking our second-generation trapped ion quantum processor, which, as you can see from the title and these pictures here, has the shape of a racetrack. This bottom movie here is actually a series of images of actual ions taken on a camera, transporting around this racetrack. And these transport operations will be pretty critical for our protocol for doing full circuits on these trapped ion qubits. So for those of you who aren't familiar, Quantinuum is a recently formed company where we just had our 2-year anniversary, formed from the merger of Cambridge Quantum and Honeywell Quantum Solutions. And as a result, we have locations around the world, and we've gotten quite large. We have around 500 employees now. Our hardware effort is based in the US, though, in Minnesota and Colorado. And the system that I'm going to tell you about today is actually just located down the road in Broomfield. So I would say in the last decade or so, there's been a realization that to truly build a large-scale quantum computer, you need the resources and funding that's available in industry. And so this chart I took from the Quantum Insider. They made this chart last year of all of the different companies in quantum computing and various aspects of quantum technology. And you can see there's a ton of companies here. There are new ones popping up all the time. Most of the full stack quantum computing companies that are actually building the full devices or the quantum processing units are located in this part of the table here. And all the different modalities are well represented, including superconducting qubits, ion traps, neutral atoms, et cetera. And I'd like to point out the front range is also quite well represented with us, atom computing, cold quanta, Vescent, and I'm sure there are many others here that are not on this chart. And this is just a snippet of some headlines that I found from a quick Google search of quantum computing, and so it's been making the news more and more in the recent years. And so I'd say there's been quite a bit of hype in the field of quantum computing, but I think there's still some pretty large challenges in the field, and namely that of scalability. And so today we're sort of entering this noisy intermediate, or we're sort of in the noisy intermediate scale quantum era. This is a term coined by John Preskill, and we need to get better on multiple fronts. And we need to push the errors down below this error correction threshold, and we also need to increase the number of physical qubits so that we can encode a large set of logical qubits to do fault-tolerant quantum computing. This is mainly an engineering challenge, as most of the basic building blocks, the single qubit, 2-qubit gates, state preparation and measurement, have already been developed and researched pretty extensively in the last several decades, probably by a lot of people in this room. There's been seminal work in trapped ions at NIST just down the road, for example. And so the main challenges are, how do we increase the number of qubits while also improving error rates? And I hope to convince you in this talk that at Quantinuum we're sort of demonstrating that, and we have a path forward to keep this trend going. So maybe just a brief word on why do quantum computing with trapped ions? Well, one of the main advantages, I would say, of trapped ions is that since we're using individual atoms, those individual atoms are perfectly identical. Now, of course, the environment that we put them in is noisy, and that sort of renders them different, but it reduces the calibration issue to an issue of calibrating the environment and not the qubits themselves. And as was pointed out in the late 90s and early 2000s, you can generate a 2-qubit entanglement, which is one of the primitive operations for quantum computing, by just putting 2 ions in the same potential well and then turning on and off lasers to turn on and off, to entangle the spin and motion and realize a quantum logic gate. Now, now to extend, obviously you want to do this with more than 2 qubits, and so to extend this to multiple qubits, one thing that people have looked at is just doing these operations in a long chain of ions. And this is certainly possible, but and by addressing the motional modes of the entire NIN chain in a very specific way, you can entangle any pair of qubits in this chain without affecting any of the others. However, as you scale up the number of ions, this becomes difficult for 2 reasons. Number 1, just the sheer number of calibrations that you have to do. And number 2, also the motional mode spectrum of this whole crystal becomes quite dense and it becomes difficult to deal with. So instead of Quantinuum, what we've focused on is a so-called quantum charge coupled device architecture. And this was actually an idea initially proposed at NIST in the late 90s. And basically the idea here is that we perform all of our quantum gates on short ion chains in dedicated interaction zones, and then we can hopefully achieve very pristine gates and then copy that performance from one gate zone to the next. So here is a schematic of the H1 trap, which is our first generation ion trap at Quantinuum. These 2 long gray bars here are RF potentials that can find the ions radially, and then we can find the ions along the axis by applying voltages to each of these segmented DC electrodes. And the gate zones here are these blue regions. And then to achieve all-to-all connectivity, we actually physically transport the ions from one zone to another by changing the voltages on these DC electrodes. In our case, we're working with 4-ion crystals, so we have 2 ytterbium-171 ions, which are our qubits. For the experts, we use the standard hyperfine qubit in the ground state manifold. And then we have 2 barium-138 ions for cooling, because it turns out to achieve high fidelity gates, you need to be pretty close to the ground state. All of these transport operations incur some excitation, as well as just letting the ions sit in the ion trap. That also causes them to heat up. But because these transition wavelengths are so different, we can cool the barium ions mid-circuit without affecting the quantum information of ytterbium at all. And so that's a nice advantage of using this mixed species scheme. So I would like to walk through a brief cartoon of how this QCCD architecture works for implementing a small algorithm. So here we have 3 qubits, red, green, and blue. And I initially want to do some single qubit Hadamard gates, and then I want to do some controlled knots between the various qubits, maybe do a mid-circuit measurement, and then reset this middle qubit here. So initially, we will apply some state preparation pulses to put the ions in a well-defined quantum state. And then we can do a single qubit gate in individual zones with co-propagating Raman beams. And then again, we need, in order to do the CNOT, that's a 2 qubit gate, we need to have the ions in the same potential well. So we'll physically move the red and green ions into the same well. And then we'll apply the 2 qubit beams. Here we address the axial mode of motion. I'll come back to that a bit more later. And then we need to get the red and blue in the same zone. And so since these ions are living in a line here, they can't move through each other. So we have to physically swap them around each other, and then we can move them into the same zone and apply another 2 qubit gate. And then we'll apply a measurement pulse to this ion here, and then we proceed with the calculation. So one thing to notice is the ions end up in a different position than they started in. And so there are no predefined neighbor qubits in this architecture. And so the operation fidelities are characterized by zones, not by qubits. This is different to other architectures where, if you look at papers from IBM or Google, they'll show charts of the fidelity of specific qubit pairs. In addition, we also have our control software also tracks the location of the qubits as they move throughout a circuit, and then any phase offsets that are accrued during a circuit. I'll come back to why this is important later. And so our universal gate set, we have single qubit rotation, which is, again, co-propagating Raman laser beams. Z rotation is actually just performed in software. And then this fully entangling 2 qubit gate, we actually have this ZZ interaction of the form shown here. So for experts in the audience, this is actually a Molmer-Sorensen gate in the phase-sensitive configuration, but then we do single qubit wrapper pulses with the same lasers, and then that renders the entire thing phase-insensitive. And from this, you can actually build up any other unitary operation. So this is all you need to build a universal quantum computer. But it turns out for a lot of applications, actually, you want to have these partially, you want to be able to control the amount of entanglement that you're generating. And so actually, our native 2 qubit gate is this parametrized angle 2 qubit gate of the form shown here. So we can vary this theta from 0 to pi over 2, which would be this fully entangling gate. And the advantage of this is, well, for one thing, like there are certain algorithms such as QFT that just this is a natural thing that you'll want to use. And the other advantage of using this parameterized angle gate is that, in the case that you do want to only use like theta not equal pi over 2, the normal way you would do this is you would do two C naughts and then a Z rotation in between. This requires two 2-qubit gates, and since the 2-qubit gates are typically the largest error in these systems, you would get twice the error from doing this. Well, actually more than twice the error. And so it's a huge win, actually, to replace this with this parameterized angle 2-qubit gate. And then more generally, there's just, I think, in a lot of algorithms, there's an incentive towards a larger number of more weakly entangling gates. So for doing analog simulation on a digital quantum computer, you typically do this thing called trotterization, where you'll break up a Hamiltonian that's the sum of terms that don't commute into alternating applications that, and then in the limit that you make the number of these chunks get to be very large, the error in doing that becomes like vanishingly small. Now, of course, you only benefit from this if the error of your parameterized angle or your partially entangling gates decreases as you reduce the gate angle here. And so this is our data showing the infidelity versus angle. Again, pi over 2 is the fully entangling. And we see that it is decreasing as we go to 0 angle. It does not go to 0 at 0 angle, which is due to some technical considerations. But nevertheless, like if you just consider, say, this point here at 0.1 pi, the error here would be 0.8 times 10 to the minus 3. If instead we didn't have this parameterized angle gate and we had to use the 2 ZZ gates, this would be twice the error of this. It would be like 4 times 10 to the minus 3 or 5 times higher. So this is a pretty significant win here. Okay, so maybe just touching a bit more generally on what are the differentiating features of the QCCD architecture. So the first is this all-to-all connectivity. Now, of course, there's no free lunch here. We have to physically transport the ions around. But in the nearest neighbor case, imagine you want to entangle these 2 qubits here. Basically, what you'd have to do is that you'd have to actually logically swap information through the grid. And so that would require many more 2-qubit gates, here around 10. Whereas in our case, we would just physically move these 2 qubits next to each other and then do a single 2-qubit gate. Now, the downside of this is that we incur errors during these transport times, but those errors are about an order of magnitude less than the 2-qubit gate error. Second thing is we have high fidelity gates in these isolated gate zones, and we can replicate that performance from one zone to the next. And so we're achieving state-of-the-art performance, and we're able to replicate that performance from one gate zone to the next. And then the final thing is we have very high fidelity mid-circuit measurement and reuse, so we can measure the quantum state of a qubit without affecting the quantum state of other qubits, and then reinitialize them into a well-defined state and continue on with the calculation. And then we also have the ability to conditionally perform gates on a classical variable as well. So just one more word on the advantage of these dedicated interaction zones. So in the H2 system, we have 32 qubits. And so this left figure here is basically just showing each line connects one of these 32 pairs here. And so there are 496 lines there. You actually get this really beautiful looking pattern. But basically, in the case where you say had a chain of 32 qubits, you would have to have 496 different calibrations of the qubit interactions. In our case, we're doing gate zones in 4 dedicated places, and so that basically means we have only 4 calibrations we have to do. And so that's a huge simplification in the overhead of the system. And then the qubit reuse actually enables us to do some cool things where you can actually simplify shallow, wide circuits to run with fewer qubits by just thinking about causality. And this allows us to, for example, this circuit here on the left is actually equivalent to this circuit on the right with 1 fewer qubit, because if you just look at where this measurement is happening in the circuit, you can put it sort of right here, and then you can reinitialize that qubit to 0, and this circuit is actually exactly the same. This has allowed us to, on the H1 system, to do dynamics of 32 spins with just 9 qubits, and on the H2 system to do optimization problems on 130 effective particles using just the 32 qubits that we have. Okay, so with that, I'd like to move on and give some motivation for the H2 system and kind of where it fits in our overall roadmap. So this is our roadmap at Quantinuum for creating a large-scale quantum computer. So we started out with the H1 system. This was released in sort of late 2020. And eventually, we'd like to move to these grid-style traps where the gates are performed on these streets, and then the ions basically move through the junctions and turn corners to be sorted. And then eventually, we'd like to integrate optics into that structure, and then maybe tile these to create a truly large-scale device. Now, one thing you'll notice is the grid-style trap is a lot more complicated. The RF topology is a lot more non-trivial. And also, you're going to have gate zones, parallel rows of gate zones. And so the H2 system, is meant to sort of bridge the gap in between those. So on the one hand, it's still a quasi-1D geometry, but it does have concentric RF rails, and it also has parallel rows of gate zones. And so it's sort of is a bridging. It allows us to bridge some of the technological hurdles that need to be overcome between the first generation and these future generations. Before I do that, I'd just like to highlight some of the amazing work that's come out of the H1 system in just several years. We've looked at adaptive quantum circuits where you can use measurement and feed forward to generate long-range entangled states and topological states, looked at the dynamics of open quantum systems, and also looked at quantum error correction of both single and two logical qubits. But ultimately, I think 2D is the way to go. And if you look at one of the initial proposals from NIST, they drew a two-dimensional architecture. So they were probably on to something at that point. And it turns out that one of the biggest bottlenecks of the QCCD is this reordering time, the amount of time that it takes to rearrange qubits from one round of the computation to the next. And so in a linear case, this just scales like the number of qubits, but in the two-dimensional case, it can scale like the square root of number of qubits. So that's a pretty huge win in terms of the sorting time. And this, we're actively working on this. So this right video here is actually an ion moving through our grid trap prototype. And then this paper from Cody Burton earlier this year kind of highlights some early transport measurements and of a junction trap device. Okay, so just briefly, a few of the technology upgrades that we have in the H2 system that are going to help us achieve this roadmap. One is a two-dimensional magneto-optical trap for loading. So this allows us to have a separate vacuum chamber where the atomic sources live, and then we can just control the atomic flux optically by turning the Mott beams on and off. This allows us to load our 32 ytterbium and bariums in several minutes, and we can reload individual lost zones in about 15 seconds. The second is we need to find more creative ways to reduce the number of signals per qubit, because this is one of the general problems of a lot of quantum computing platforms is just the sheer number of signals that you need to address the qubits. And so in the curved sections of our trap, basically we're only storing ions. We're not trying to do any gates. And so we don't really care that exquisitely about the potential. And so we can actually just tile the electrodes in a repeating pattern ABC so that all the A electrodes are connected, all the B electrodes, et cetera. And then with just 3 signals, we can actually get 20 potential wells. And so, for example, if you apply a positive voltage to the A and C and a negative voltage to the B electrodes, you can get ions trapped over all the B electrodes. And the final thing is, because we have these concentric RF rails with DC electrodes tiling the perimeter, the RF has to burrow into the trap to connect to itself. And this is going to be necessary for these two-dimensional traps where you have many different RF islands and streets and stuff. Okay, so similar to the H1 trap, the H2 trap, we're still using ytterbium for our qubit, barium-138 for our coolant. We're still working on laser-based gates on 4-ion chains. We're still using ion transport to achieve all-to-all connectivity. The main differences are really just the periodic boundary conditions and the 2 rows of gate zones. So zooming in here, the gate zones are these regions here with the skinny electrodes. And for this work, actually, we're only going to be doing quantum gates on one side of the trap, although we're doing the physical swapping operations and transport on the entire trap and on both rows of gate zones. Okay, so now I'm just going to briefly describe how we actually do the operations in this device. So each of these circles here is a 2-ion crystal, so it's a ytterbium barium. And when we do 2-qubit gates, we do them in a particular crystal order. So we always have ytterbiums are the large orange circles, so we always do 2-qubit gates on a YBBY crystal. And then when we address the axial mode of motion, one of the axial modes of motion to do the 2-qubit gate. For the single-qubit gate, we would split this into 2-ion crystals and then move one of them to the center and then apply the co-propagating Raman beams And then for the measurement, we do a similar thing. We also intentionally apply micromotion to the unmeasured ion to minimize the amount of absorption of scattered light. And then in the storage regions, we alternate between a YB crystal and a BY crystal to keep the pattern consistent around the racetrack. And then the other thing worth pointing out here is related to the parallel rows of gate zones is basically these gate zones are arranged in a square grid so that in principle, the beams that are aligned to this bottom row of gate zones, if they were perfectly aligned, they would also be aligned to this top row of gate zones. And it turns out that's actually quite difficult to do, so we kind of save that for future work because we need like less than 1 micron. We have like less than 1 micron tolerance on those alignments, and so that's like quite difficult to achieve. But to avoid unwanted entanglement, just because they're probably reasonably well aligned in hitting this region, we actually move these crystals in the upper gate zone out of the way when we do gates here. But it's worth pointing out that so right now here I'm showing 4 sets of beams. If you just added 2 more total beams for 5 pairs, you would basically be able to, in principle, address all 8 gate zones. And in the grid trap, you could address, in principle, like many rows with reusing the beams. And so that's another sort of thing that we're thinking about for future architectures. This turquoise and yellow beam here, these are Doppler cooling sheet beams that illuminate the entire trap. And these allow us to cool barium mid-circuit to keep the ions near the ground state. Now, when we load ions, we have this small load hole over here. We load individual ytterbium or barium ions, and then we transport them one at a time and combine them to create a 4-ion crystal in this first gate zone here, and then we move that on its way, and then we just keep repeating that process. And we also have a procedure for if we lose an ion in one zone, we can basically only have to reload that zone, but that's a bit more involved. Okay, so it's useful to think of our 32 qubits as being part of 4 batches of 8 qubits, so I've color-coded them here. And so initially, we bring the left qubits to the center, and then we have the option of doing single qubit gates. So here I'm showing a gate on all qubits, but we can do any subset that we like. And then we do the same thing for the right qubits. And then we combine into 4-ion crystals. And then we apply the 2-qubit beams, again, in any combination of zones that we like. And then we would just repeat this 4 times to gate all 32 qubits, as desired. I mean, we might not need to gate every single pair depending upon the circuit. Okay, so that's kind of like the easy part. Now the hard, well, I wouldn't say that's the easy part, but that's reasonably straightforward. But now the hard part is how do we maybe in the next round we want some of these purple qubits to interact with the yellow or blue qubits, for example. And so to do that, again, since this is a quasi-1D architecture, we have to still rely on physical swap operations. So we'll initially do some swaps maybe in these zones here, and then we'll bring in one of the blue qubits and one of the purple qubits, and then we'll do some more swaps. And then we'll bring in more of the purple and blue qubits, and then we'll do more swaps. And you can convince yourself that if you do this enough times, you can basically achieve whatever arbitrary ordering you like. Now, one thing we care about a lot is memory error. And so, all of these transport operations take a lot of time. And there can be a variety of things that can happen to the qubits that during that time that cause errors. And so, for example, maybe initially we do a single qubit gate on a qubit in this zone right here. And then later on in the circuit, it's located over here, and then maybe over here. And then finally, we want to do another single qubit pulse in this other zone over here. And so we need to very carefully track the location and any phase shift accrued by that qubit, because otherwise we would, maybe we think we're applying an X pulse here and really applying a Y pulse or something like that. And so, and then, additionally, the qubit could leak out of we could have leakage out of the qubit subspace. We could also have one of these swaps could fail, and then we'd be doing operations on the wrong qubit. And so we lump all of these together into what's called memory error. And I'll show you data later that sort of characterizes this. But a couple things that are important are we need to measure the optical phase difference between the SQ beams and the different gate zones, and then we also have to track the qubit frequency around the trap so that we know what phase shift to apply. Okay, so with that, I'd like to switch gears and talk about how we actually benchmark the system, because thus far I've just shown you that we have a device that has 64 trapped ions, but we want to know, is it actually useful? Because as an analogy, if you had, say, a 100-person airplane, but it can't take off, then it's not really an airplane. It's just a bus. And if it can't taxi, then it's not a bus. It's just a room. So we want to basically show that we can actually do algorithms, useful algorithms, with all 32 qubits. Taking a step back to classical computing, there's a hierarchy of benchmarks that you could do. So you could benchmark the components of your computer, such as how fast is the processor. You could benchmark at the system level, which is how does the processor interact with the memory. But ultimately, what a customer actually cares about is an application level benchmark. So like, how well does it play your favorite video game or something like that. So similarly, in the quantum case, we have a similar level of hierarchies. So we have component level benchmarks, which is what is the failure rate of the individual gates. And so these things involve 1 or 2 qubits typically. We have the system level, which is more complex operations that involve all of the qubits. And then we have the application level, which is indicative of actual user algorithms. OK, so first I'll go through the component level benchmarking. And so for this, again, since we're only doing the quantum operations in this lower row of gate zones here, we focus on just those 4 zones. And in general, we use a technique called randomized benchmarking, which is basically you apply a sequence of m gates, generally chosen from like the Clifford group, so that like it has a well-defined inverse, and then you just apply the inverse gate. Now, if there were no errors, this would basically this whole sequence would do nothing. It should just be the identity. And but there are errors in real life, and so like you actually see the probability of measuring the correct outcome decay, and from that decay you can extract out the error rate of the particular gate that you're looking at. Now, I don't have time to get into all of the different benchmarks, but this is a summary of the component level benchmark. So we looked at single qubit randomized benchmarking. So this gives an error of a few times 10 to the minus 5, and the 2 qubit randomized benchmarking is about 1.8 times 10 to the minus 3. Now these leakage things here, this basically you can set up an experiment where you measure the contribution on a per qubit basis to either the single qubit or 2 qubit error of leakage out of the qubit subspace. This mainly just comes from like Raman, scattering from the Raman beams, or spontaneous emission from the Raman beams. This 2 qubit SU4 randomized benchmarking, that's doing arbitrary unitary operations on 2 qubits, and so this involves, I believe, 3 2 qubit gates of less than pi/2 angle, so it's not 3 times the error of this, but we looked at that one. I've already shown the data for the parameterized angle benchmarking. This transport SQRB is what we use to measure the memory error, and so that's like about an order of magnitude less than the 2 qubit randomized benchmarking. And then this measurement and reset is related to the probability of inadvertently measuring or resetting a qubit that you didn't intend to measure or reset. And that's sort of at the part per million level. And then this final one, state preparation and measurement, this is the error of falsely identifying qubit state 0 as 1 or 1 as 0. And for our system, this is actually dominated by the measurement error. So a few things I'd like to point out with the component level benchmarking. First, regarding the 2 qubit randomized benchmarking, is that we looked at the infidelity of the individual zones, which are the dashed curves here. And then we also looked at the average, which is the solid here. You'll notice that there's a very tight spread between the different zones. So we achieve almost the same performance in all 4 gate zones. And so this really highlights the fact that we're replicating our performance from one gate zone to the next pretty reliably. OK, the second thing we looked at is this, second thing I'd like to point out is this transport single qubit randomized benchmarking. And so this is what we use to measure the memory error. So basically, a standard, any arbitrary quantum circuit in general is going to basically look like of the form shown here. So it's basically going to have SQ gates on as many qubits as you want. I mean, here it's just showing on all, but SQ gates on whatever qubits you want, and then 2 qubit gates on pairs of qubits, and then a permutation to reorder the qubits. And then you just repeat that over and over again. Now we define a def1 circuit time as sort of the average time that it takes to do one of these chunks. And of course, there's some variation depending upon how much permuting you have to do, but nevertheless, we can kind of define like an average time here. And so basically what we do to measure the memory error is we take advantage of the fact that this single qubit randomized benchmarking error is quite small. It's like it's a few 10 to the minus 5. And then we just basically perform this circuit with random permutations here every round so that we kind of just, qubits kind of are moving all over the trap in random places. But we just don't do the 2-qubit gates. We would do all of the cooling pulses that we would do before gates, but we don't actually perform the 2-qubit gates. And then we just look at the probability of measuring the correct output as a function of the sequence length. And from that, we can fit this memory error of around 2 times 10 to the minus 4. Now, it's worth noting this is a memory error per qubit. So, and the fact that this is linear also supports an incoherent scaling of memory errors. So, in other words, if you have epsilon 1 at time t1, then you would have, after n of these depth 1 circuits, you would have just n times that error. And in this incoherent limit, you can actually, like, roughly speaking, define an effective 2-qubit error, which is just the 2-qubit error you would get from the TQRB plus twice this memory error. And so, this effectively contributes sort of like 4 or 5 e minus 3, 4 or 5 e minus 4 on top of this 1.8 e minus 3 2-qubit error here. Okay, so next I'm going to move on to the system level benchmarking. And here the main thing that we want to test is, that if we just take the error rates that we measure from our component level errors and then sort of scale them in the appropriate ways, that we can predict the errors that we would get for these system level tests, just to verify that there are no gaps in our understanding of our error model. And I'd like to emphasize that we're doing a set of benchmarks which is introduced by other groups. So we're not just cherry picking a benchmark that we think we're going to be do really well at. And so, for example, mirror benchmarking was introduced by Sandia, quantum volume by IBM, random circuit sampling by Google, and later by Susung Ji. And then this GHZ state is a common thing that is looked at in academia and industry. Oh, and the other thing I'd like to point out is for these first 3 benchmarks, basically from the data, we can extract an effective 2-qubit error rate and then compare that with what you would expect given the average angle of the 2-qubit gate involved. So the first thing we looked at is mirror benchmarking. So here, basically, you perform a circuit where each of these orange blocks here is basically a random single qubit gate applied to each qubit, and then a fully entangling 2-qubit gate. And then you permute the qubits, and then you do this up to sequence length n, and then you apply the mirrored circuit in the second half. So you would apply all the inverse 2-qubit gates, and then all the inverse SQ gates, sort of in the backwards order. We also, for experts in the audience, we also do this thing called Pauli twirling, where we sort of sandwich this whole thing with SQ gates and this sort of minimizes the contribution of coherent errors canceling throughout the circuit. So at the end of the day, basically this whole thing should give you the identity, and so we apply a random set of Pauli operators at the end to randomize the correct output. So there's basically one correct bit string that we should measure at the end of the day. And so then we can just look at the fidelity of getting the correct output as a function of sequence length for different numbers of qubits. And for larger numbers of qubits, for the same sequence length, there are just more gates because there are more total gates in the circuit, and so you would expect this survival to go down. It still kind of amazes me that for 32 qubits, there's 4.3 billion possible outcomes, and so sort of even after the sequence length 10 corresponds to several hundred gates, we're still measuring 30% chance of getting this correct output out of 4 billion. And so from this data, you can actually extract an effective 2-qubit error, which includes single qubit error, 2-qubit error, and memory error. And we find that this is basically consistent within the error bar as we increase n, the number of qubits. And so this is really encouraging and really supports our claim that we're increasing the number of qubits and keeping the errors constant. Next thing we looked at is quantum volume. So this is a similar circuit structure. It would actually be a square circuit on n qubits. So if you have n qubits, then you run n rounds of this thing. So for simplicity, I've just shown 4 qubits here. And so here, the orange blocks are actually SU4 operations on 2 qubits. And so that involves multiple 2-qubit gates and multiple single qubit gates. And again, random permutations between the rounds. And so basically, you run this circuit, and then you measure some output bit strings, and then you compare with a classical simulation. And so clearly that's not scalable as you increase the number of qubits because you have to do a classical simulation, but nevertheless, it's still a very difficult benchmark to pass for short-term devices. And so the way that you actually assess the performance here is that you order the bit strings from least probable to most probable, and then you define the heavy outputs as those with a probability greater than the median. And then you just compare the experimentally measured heavy output probability with the ideal case. Now, for a fully depolarized circuit, in other words, if you just had complete noise, you'd expect 50% of the time that you'd have a heavy output. And the large n limit, the ideal heavy output probability averaged over many random circuits goes to about 85%. So it goes between, your data should fall somewhere between 50 and 85%. And so it was pointed out that 2/3 is kind of the passing threshold. So basically, if you can, like we ran this averaged over 200 random circuits, and basically after 200 circuits, our confidence interval exceeded 2/3 of 2 sigma confidence. So we can say we passed the quantum volume for n equals 16. Of course, it's one of these weird things that's defined exponentially. So it's actually, we say we have quantum volume 2 to the 16. From this data, we can pull out an effective 2-qubit error, and I'll come back to that in a minute. But this bottom plot here, sorry for it's kind of small, but it basically shows over time the progress of the different quantum computers at Quantinuum in measuring quantum volume, with the H2 system being the orange points on here. This dashed line is actually this 10 times per year. It's kind of like a Moore's law type thing, where we had promised we had made this promise when we were still part of Honeywell that we would increase the quantum volume by a factor of 10 every year for the next, I think, 5 years from 2020. And we've pretty much held true to that. And since then, the H1 system has actually gone beyond this 2 to the 16. But anyway, this just sort of shows that we're consistently making progress in building these devices and making them higher quality over time. The third thing we looked at is random circuit sampling. So this is something that was done by Google and Susong Ji, which is a Chinese collaboration in the context of quantum advantage. You may remember this quantum advantage paper from Google back from 2019. And so to kind of compare with what they, just to kind of compare our system with theirs, we basically ran a similar circuit with a similar geometry. So in their system, they have superconducting qubits in a 2-dimensional grid. So I mean, we have all-to-all connectivity, but nevertheless, just for a fair comparison, we did the 2-dimensional case. And so here, basically, it's just like the circuit is just you choose single qubit gates randomly from some set, and then you apply 2 qubit gates in this tiling pattern, kind of like this. And then you measure this quantity called the cross-entropy fidelity, or cross-entropy benchmarking fidelity, which is basically related to the mean probability of measuring the outcomes that you measured. And so again, this also requires classical simulation, so it's pretty difficult. It's also not scalable as you increase n too large, but it's still nevertheless is a good benchmark to look at. And we can also pull out an effective 2-qubit error from this experiment as well. Finally, we looked at GHZ state. So GHZ state is a very sensitive test of qubit coherence. It's a superposition of all zeros and all ones. And so we can prepare this in 2 different ways. We can either do a unitary circuit, which is just you do a pi/2 pulse, and then you just do a bunch of C naughts on basically bringing 1 qubit in with each C naught into the GHZ state. We can also do it adaptively, and this adaptive preparation is pretty interesting because in the limit that you have enough gate zones and you can do all of the gates in parallel, it actually allows you to prepare long-range entangled states in fixed circuit depth. In our case, it actually requires more. It requires mid-circuit measurement and feed forward, but it actually requires more gates. So then to measure the fidelity of the GHZ state, we look at the population in the all 0 and all 1 states. Again, for n equals 32, there's like 4 billion possible states here, and then we also measure the coherence in n+1 possible measurement bases, and from that we can extract 82% fidelity for the unitary prep and 74% for the adaptive prep, and both of those certify genuine n-partite entanglement. And as far as I'm aware, this is a world record for the largest GHZ state ever produced. So now going back to this question of whether the errors from the component levels translate into the system level errors, here is a table for each of these benchmarks of the average angle of the 2-qubit gate involved, the predicted effective 2-qubit error rate, and that inferred from the data. And basically, for each of these three cases within the error bar, we find that these agree. And so that says that we have a pretty good understanding of our error model. But nevertheless, we went a step further and then also looked at our system, how well it performed on various applications that are more indicative of like what our customers would want to run over the next several years. And so for that, we chose 4 different things which highlight different strengths of our experiments, or of our system. So for example, the parameterized angle gates, low measurement crosstalk, high fidelities and connectivities, and qubit reuse and reset, and the interaction between the quantum and classical processor. So the first thing we looked at is Hamiltonian simulation. So here, what we're doing is we're simulating a 1D transverse field Ising model with periodic boundary conditions. And so the nice thing about this is that it has an exact analytical solution, and so we can just compare to theory directly. And basically, we just initially prepare all qubits in the plus state, which is with j equals 0 as an eigenstate of the Hamiltonian, and then we just quench to a finite value of h over j and let it evolve in time. Now, since here we're basically doing sort of an analog simulation on a digital quantum computer, we have to do trotterization. So this is necessarily going to involve these, theta not equal to pi over 2 gates. And so we can basically look at the performance like using the naive decomposition, which is the green points, using the 2 C naughts and then the RZ rotation, compared with the native arbitrary angle gate, which is the orange points here. We see much better agreement in that case, which highlights the advantage and the increased performance that you get with using these parameterized angle gates. The next thing we looked at is a so-called holographic quantum dynamics simulation. So here, basically, what we do is we're using mid-circuit measurement and reset to basically simplify the time evolution of like an initial correlated state. So basically recasting a circuit that would nominally involve L qubits and go out to circuit depth T into a circuit that requires only T qubits and then goes out to length L. And so basically what we're doing here is we initially create a matrix product state, and then we evolve it by a kicked Ising model. And that has an exact analytic solution in the limit that that the number of lattice sites goes to infinity. And so then we can basically measure this correlation function as a function of distance between effective sites on this lattice as a function of different evolution times. And the solid curves here are basically the exact theory. So it's not just, and it fits the data incredibly well, even for this t equals 24 point, which corresponds effectively to a simulation on 152 spins. Each of these little bars here, which are almost indiscernible to see, represents a 2-qubit gate. And so this circuit has 2,000 2-qubit gates over 100 mid-circuit resets. It takes about 20 seconds per shot, and also caused a lot of ion loss and heartburn for the experimentalists. But nevertheless, we were able to run it, and we were able to get like pretty good results. I think that was really exciting. The next thing we looked at is QAOA, which is the quantum approximate optimization algorithm. So this is a near-term algorithm for solving optimization problems on a quantum computer. And here we specifically looked at the max cut problem, which is related to basically partitioning a graph into 2 different subsets, such that into 2 different sets of vertices, such that the number of edges connecting vertices between the 2 sets is maximized. But basically the idea here is that you encode some combinatorics problem into a cost Hamiltonian. So these Cij coefficients sort of represent some quadratic problem that you want to minimize. And basically, at the end of the day, this is just a variational algorithm. And so basically, you choose some values for these beta and gamma parameters, and then you would compute the expectation value, measure the energy, feed those values into a classical optimizer to generate new guesses for beta and gamma. And ideally, you'd want to repeat this up to p rounds. But the problem is that each time you alternate between these 2 Hamiltonians, it just requires more and more gates. And so there's a trade-off between solution quality, which requires like higher p, and decreased fidelity, which wants lower p. And so we were actually able to see an improvement with 2 rounds of this, as evidenced by the blue points are below the dashed green line. And this is only possible because of our high 2-qubit fidelity. And the final thing we looked at is this repetition code. So this is half of a quantum code because it can only correct either bit flip or phase flip errors, but not both. But nevertheless, it still captures a lot of the features of full QEC codes. The nice thing that we could do here is that we have 32 qubits, and so Google was able to go to distance 21 using 41 qubits. So we were actually able to go to distance 31 using 32 qubits by basically using one ancilla that was consistently measured and reset to measure the syndromes of all 31 qubits. And then we basically perform the decoding the same way we would want to do it when we actually do a full QEC code. We see that as we increase the distance, we achieve a higher logical fidelity. And we're also able to, from the full data set, sort of just reconstruct the information for the lower distance codes from the full distance measurement. Okay, and then the final thing that we looked at, this is kind of a separate study, was that we looked at non-abelian topological order and the resulting anyons. And I'm by no means an expert on this topic, but this goes back to a proposal from Kitaev from the late 90s that an alternative paradigm to fault tolerance is topological quantum computing. And the idea here is that basically if you take anyons, which are the quasi-particles in 2D, and you braid them around each other, that can implement quantum logic gates. And because these anyons are, because you're doing a because of the topological nature, they're just much less sensitive to noise, and so you should be able to achieve fault tolerance much more easily. And so there's been quite a bit of work on abelian topological order, but it's thought that you need non-abelian anyons to actually achieve a universal gate set. So we actually used an adaptive circuit to prepare the ground state of 27 qubits on a Kagame lattice, which has non-abelian topological order with greater than 98% fidelity per site. And then we implemented a quantum bit flip by braiding these anyons around each other. And then we did this Baromean braiding sequence, which kind of has this famous form shown here, where if you were to cut any of these three rings, the whole thing would basically fall apart. Now, if you were to do this experiment in put this in an interferometer and do this experiment with abelian anyons, you would get no phase shift, but you get a pi phase shift, which is what we would measure, which is what we measured for the non-abelian case. For more details about that, I would recommend that you check out this paper here, which is going to appear in Nature. Okay, so with that, I'd like to just point out the H2 system was released earlier this year in May of 2023, and already we've had many papers come out using the hardware, 3 internal papers and then 2 from our collaboration with JP Morgan Chase. And I think there's many more exciting things to come. And so with that, I come to the end. I hope I've convinced you that with the H2 system, we're scaling high-quality qubits at Quantinuum. We have state-of-the-art error rates, all-to-all connectivity, mid-circuit measurement, qubit reuse, this parameterized angle 2-qubit gate. And perhaps the most important thing is, I think with our recent paper, I hope we've sort of set a new standard of transparency in the quantum computing industry with benchmarking and releasing a quantum computer. And we plan to upgrade the H2 system to greater than 50 qubits in next year, which should put us in the quantum advantage regime. And so stay tuned for updates on that. Of course, this work I've had an amazing team of people to work with in this project. I think you'll probably recognize a lot of these folks who either went to, all 3, actually all 4. Yeah, so let's see. John Gabler was one of Debbie's students. Mary was a postdoc at NIST, and then Sarah and I are from June's group, Juan and Brian from Debbie's group, and then Russ from Eric's group. And so there's a lot of JILA alumni in this list and at Quantinuum in general. We've also had a great theory team that we've collaborated closely with. I think a lot of these people will also look familiar to a lot of you, probably Charlie and Carl, and probably a lot of people know Mike Fosfeig and Dave Hayes. And this is the offer list for the benchmarking paper, and as you can see, there's almost 100 people on it, and so this is really truly a huge team effort, many engineering teams involved. It still amazes me to this day that it all came together and that it worked so wonderfully. So with that's the end of my talk. If you want more information, you can check out the link here. If you're interested in joining us, we're likely going to be hiring some some more folks in next year, so maybe come talk to me or check out this link here, and I'm happy to take any questions you have.
Questions? Yes.
So are the arbitrary 2-qubit phase rotations implemented via just amplitude shaping of the lasers, or is something else going on there?
So I forget the exact procedure, but basically you can reduce the amplitude up to a certain angle, and then you have to start. I think we reduce we also changed the detuning and other things as well.
Okay.
And I think we always keep one of the two lasers on, just for technical reasons. So that's one of the reasons why that error goes at 0 angle is non-zero.
I see.
Because we still get some spontaneous emission from those.
So it's not kind of this like Chris Monroe style where they do kind of a arbitrary pulse sequence to close all their loops in phase space every single time. Or no, okay.
No, it's not like that.
For one data, you said single shot takes 20 seconds. That data was like full of mid-circuit measurement. Is the loss mainly from mid-circuit measurement, or transport also has a lot of loss? And for other benchmarking data, what is the typical shot time for?
Yeah, that's a really good question. So I don't think we have any evidence that the mid-circuit measurement induces more loss. I think it's just kind of like we have a fixed, just due to vacuum pressure, we have a fixed loss rate of a few minutes or something like that, sort of mean time to lose one of the 64 ions. Now, of course, doing transport, I think you have more probability of loss. I think the thought there is that if you have a collision, say during a swap operation or something, then that gives you a higher probability of loss. I would say that's still not super well understood. But in general, I would say we always operate our system in a way where we sort of run a number of shots such that we do a bunch of pre-checks at the beginning to say everything's good to go, it's in the correct order, everything looks good, and then at the end we'll measure the number of ions that they're in the correct order, that the B field didn't change by too much, etc. And we typically choose the amount of time that we run data for to be such that we get a say 80% probability of having all of our checks come back in the affirmative.
Thank
you. So especially with going up to 50 qubits, it seems like you'll be pretty close to a point where you could do a break-even demonstration. And I'm curious if you do that, what code you would use, because you wouldn't necessarily want to use a surface code because it doesn't seem that amenable to this geometry. But presumably you guys are thinking of other codes.
Yeah, that's a really good question. I think the theorists are trying out a lot of different things, and I think the confounding factor for all of this stuff is that the way in which our compiler converts a set of primitive instructions into the actual sequence of operations on the system is somewhat non-trivial, and so we have to keep that in mind as well. And so the jury is still out on what code we'll actually use, and I think I actually don't even really know if we decided which one we want to use.
Thanks.
It's with PMT, and we can do it in parallel in the 4 gate zone, so we can measure 4 qubits at a time.
For the GHZ state, how do you verify there's coherence between the two superposition states? Between the two
we did that
components?
parity measurement. I kind of glossed over it. So we measure the spin parity along the n+1 different. I forget exactly how this works, but basically you measure the spin parity along this axis pi k times pi over n. And if you do that for all n+1 possible angles, you can basically reconstruct the full trace of the density matrix, or the full coherence in the density matrix.
Actually, maybe I'll follow up a little bit. This may be a little bit unfair question. You didn't mention error correction at all. And what's your take on error correction? Is this important or not important? And the reason why I'm asking this, you have some competitors right now coming up on neutral atoms, which is, frankly speaking, a lot easier to move atoms around. They have
That's
2D
true.
geometry, and you have to swap the ions around in the 1D system. And so in the neutral atom system, people are starting to implement error corrections in the quantum computing in trapped ion. As you scale up to 50 ions, do you think error correction is important or not in the future?
I mean, I think error correction is definitely like the future of quantum computing. Now, I think in these quasi 1D or quasi 1D architectures, it's really hard because for the reasons that you're mentioning. Now, I mean, that's another reason to go to 2D in addition to this speed up that you get from the rearrangement time is just like it looks a lot, the qubits are just arranged in a way that looks more like a surface code or something like that. But yeah, I would say that like for us right now, sort of QEC, these memory errors, like they don't seem like that big of a deal, but they are actually a pretty big deal for QEC. And so that's like one of the things that we're going to be continually battling and trying to get QEC to like break even.
I guess Didi has something to say about it.
Not really. So I think if you talk about memory errors, then you're not using the best qubit, because it would be a truly first order insensitive qubit, while yours, you're at a finite field and it's not.
No, that's definitely true. And I mean, in the future, we're thinking about different qubit species and stuff like that.
And then more generally, if you talk about break even, the nice thing and trouble with atomic qubits is that the memory error is really, really small if you do it right.
Yeah.
It's really the operations that you need to correct at the end of the day. And so there's not just one error correction. There are sort of different flavors. And so there's a lot of subtlety to all these questions.
One more question up there, right? Yes.
Hi, thanks. I was just wondering, like, what is, say, the average duration that it takes to do kind of an arbitrary ion reorder? And like during a typical operation, what percentage of the time is spent like just reordering, like swapping the ion?
So our def1 circuit time for the 32 qubits is around 50 milliseconds.
Okay.
And so that includes the gates and the cooling time. And so depending upon what kind of circuit we're doing, it can be transport dominated, such maybe like 70% transport, like 30% cooling, and then and then it ends up being like 1% or less actual time doing gates.
Mm-hmm.
So yeah, we spend almost all of the time doing transport and cooling.
Okay, thanks.
Any more questions? Stephen has become this amazing scientist and technologist, and yet he speaks still just as fast as when he was a graduate student. But that's what was great is we got a lot of time for questioning, and we can end the colloquium right on time at 5 o'clock. One last question. If not, let's thank Stephen one more. Oh yes, one more question.
This is just a sort of silly question, but in the you had that movie of the ion running around.
Yeah.
No. In the grid.
Oh, in the grid. Yeah.
Yeah. Is the fluorescence beam like tracking the ion there? Is that did I get that right?
I didn't make that movie, so I can't say for sure. But like, I can tell you that a lot of these traps have these sheet beams which illuminate the entire trap, and so like you can basically image the entire thing.
Okay.
All at once.
Okay. Thanks.
And that we would do with the camera, not with the PMT.
Okay. Thank you.
But of course, you're doing this only for the illustrative purpose.
Only for illustrative purposes, yeah. I mean, at the end of the day, we never use the camera for anything in an actual quantum circuit. Oh yeah, they go way faster than that. Yeah. Yeah, that's right.
Okay. Well, let's thank Stephen one more time. Great talk.
Thank you.
That was very nice. It's amazing. So, error correction is being difficult.